Okay, I'm out here with our 2.5-inch custom build on ArduPilot, and I'm going to do its first flight. We're going to take a look at the logs and see how the vibrations look, and we're going to use those logs to set up our other parameters. I'm also going to try to switch this into altitude hold mode using the barometer, and we're going to see how well it works. It's a little bit windy out here, so I think we're going to get a little bit of drift, but we'll deal with that, assuming that it's basically flyable. So the first thing we're going to do, let's go ahead and put it down. Let's power it up. And hopefully you'll be able to hear this in the background, but it's doing its startup beeps. ArduPilot takes a little bit longer to boot up than Betaflight. It's not terribly long. All right, it's booted up. Let's go ahead and hit the arm switch, and there is a little bit of an arming delay. It's about 2 seconds before it actually arms the motors. Here we go, let's take off. All right, so it's drifting a little bit in the wind, but it's basically flyable. No visible oscillations. I'm in stabilized mode, or that'd be angle mode for Betaflight users. It's basically flyable. Probably a little bit of tuning that we're going to end up doing in a little bit. But like I said, no visible oscillations. What I mean by that is it's not shaking out of control. Let's switch to altitude hold mode and see how it does. All right. So I got a little bit of drift here. I have my left hand off the throttle. Let's try to bring it back in the camera here. So I have my left hand off the throttle. And what it's doing right now, if you remember, we set the hover learn to 2. So it's learning the mid-throttle hover value. You can see it's struggling in the wind here a little bit. And I am adjusting the throttle to come back to the middle position, and it's using the barometer to hold its altitude. So I am just giving it some pitch and roll, trying to counteract this wind. ArduPilot really only needs about 30 seconds for it to learn the hover value, but I'm going to give it a little bit longer here because we're in this wind. So it should be settling in on a hover number. We're going to take a look at that off screen here. Okay, I'm going to switch back to stabilized mode. I'm just going to zip it around a little bit. And let's go ahead and land it. We'll disarm, and we'll see you back on the computer screen. Okay, welcome back. So we completed our initial test flight, and we tested the altitude hold. Now what I'm going to do is take a look at the log files from that initial test flight, just to see how things are looking before we start tuning. So the next thing we want to do is download the log files off of the flight controller. One way to do that is to use Mission Planner. I like to use Q ground control because I find that Mission Planner takes forever to download the log files, while Q ground control seems to be much faster. So go to Google, type in Q ground control, click that first link, and you can download off of their website. Let's fire Q ground control up on my computer. So in order to download logs, we're going to click the Q icon up in the top, Analyze Tools, Refresh. And because we don't have a GPS connected, it doesn't get the timestamp, so we're going to download the first log. It should be the only log because this was our first flight. Check that box, hit download, find a place on your computer to save the file. So I'm going to download files. In the background, you're going to hear Q ground control complain about some fail-safes. All right, the file is downloaded. I'm just going to erase the logs, hit yes, and then we can quit the program. Okay, there's 2 ways to review the logs. The first is using the UAV log viewer. This is on ArduPilot's website. You can drag and drop files in here to view the logs, or you can use Mission Planner. So let's find the log file that we just downloaded and drop it in here. The first thing I'm going to do is I'm going to look to make sure that there's no excessive vibrations. So let's go down to the plot individual field. I'm going to scroll all the way down to vibe 0, expand this, and I'm going to take a look at the VibeX first. And you can see here that it's logging the vibrations for the entire duration of the flight, and you can see the different flight modes. So for stabilize, and then we switched to altitude hold mode for the hover learn, and then we went back to stabilize, and then we landed. So you can see that it's hovering in around the 2 up to about 7. Let's remove this. Let's take a look at the Vibe Y, and this is pretty consistent around 2.5 to 3 for the duration of the flight. And then we'll take a look at the Vibe Z, and you can see here we have around 8 to 9, and then spike as soon as we tried to land. What we're really concerned about here is the average, so we can see that this is under 10. Okay, so if we go over to Google and type in ArduCopter methodic configurator, and then you type in tuning_guide_ArduCopter, click that first link, and it's going to take you to the documentation for a tool that ArduPilot developers put out called Methodic Configurator. We're not exactly following this tool step by step, but something I wanted to point out, if we scroll down and we arrive at this section, vibrations over 30 are bad, and vibrations below 10 are good. Okay, the next thing we're going to look at in these logs is the actual output oscillation. So let's remove the VibX. We're going to come up to RCOU, and now we're going to plot RCOU C1, C2, C3, and C4 for the motors. And you can see here on this chart that the oscillations are ranging anywhere from 1300 to 1500. So coming back over to the configurator page, this is an example of some severe output oscillation. This is for a 4-inch quadcopter in this graph from the documentation. And you can see here, if we scroll down below, this is what a corrected output would look like. So it's oscillating in a very small range. Going back to our UAV log viewer, we do have some more significant oscillation that we're going to need to correct before we move on. So we're going to take a look at that next. Okay, we're back in Mission Planner, and we want to start looking at parameters to change in order to correct the oscillations that we just saw. Let's take a look at our motor hover value that we had learned during the altitude hold mode. So we type mot_th. You can see that our motor thrust hover value is now this 0.231. So let's keep that in mind. Here we're looking at the initial tuning flight page, and if we were to scroll down to the test altitude hold mode section, it has us setting the PSC_ACCZ_I to 2 times that value that we just saw, and then the _P to 1 times that value. Let's go back over to Mission Planner. Let's set this to 0.46 and then P to 0.23. Let's write parameters and let's do a test flight and see. All right, so I did a test flight changing those 2 parameters alone, and I have plotted here the RCOU C1 results for that test flight. Let's compare that to the first flight for RCOU C1. That first flight, you can see that there's a little bit more variance, and then after tuning those 2 parameters, you can see that it's really starting to kind of settle in, especially down here at the bottom of the screen. It definitely looks more like the one on the documentation page. So on the new flight with the 2 change parameters, C1, 2, 3, and 4 along the bottom here and up top. So it does look better. Those 2 parameters did definitely improve the oscillations showing up in the logs compared to the first flight. So now we can move on to the next step. All right, so we're back in Mission Planner, and we're going to start setting up our harmonic notch filter. This is going to help filter out noise making its way to the flight controller. Let's search for ins_log bet_mask, set the bet mask to IMU1, write parameters, and we can disconnect. We're going to do a test flight for about 30 to 40 seconds to collect data, and we'll be right back. All right, we're back after doing our test flight, and we downloaded the log file in between video clips. So let's go take a look at those logs and set up our harmonic notch filter. I open up Google, and we're going to type in ArduPilot filter review tools so that we can take a look at the logs in a different way. We choose the log file that we downloaded between video. All right, let's scroll down here. We're going to take a look at the gyro here. So we have 2 peaks. Sometimes you'll see a peak early, sometimes you'll see some peaks late. In this case, we just see 2 peaks that are nearby. So what we're really wanting to do is we're wanting to filter out these 2 large sets of noise and flatten them out using filters. So if we look at the first peak, this is typically the first notch that we're going to want to filter out. You can just hover your mouse just like I am doing right here, and you can take a look at the amplitudes for this. So right here we're seeing a peak of 323, and then we can slide down. So let's keep that in mind. We're right around 320, 325, and then if we take a look on each side of the peak, 290 to 295, and then maybe 340 to 350. So if we think about that, that'd be 325 with 25 hertz on either side. So keep that in mind. We're going to scroll down here, and this is where we can set up our filter configuration and test it out before we actually do it. So let's try to enable this. We're going to use ESC telemetry based filtering, and we're going to type in that frequency that we just found above, 325 hertz, make it a little bit bigger for now. Let's call it 30 hertz. Down here we can see options for first harmonic, second harmonic, third, etc. Typically you're going to see these up here where the first harmonic is at the first peak, 325 hertz, and then the second harmonic would typically be at twice that value, so 650 hertz way out here, and then the third harmonic is going to be times 3. You're going to see this with the number of blades passing the motor arm. So if you see here, you're going to have the first propeller, second propeller, third propeller for a 3-blade prop. Sometimes you won't. So we don't see this out here, so we don't need a second harmonic. We can recalculate the filters, and then we can go up here and see what it would do. So you can see that it flattens out this peak right here. We still have the second peak, which we can deal with later. Scrolling down, we see the actual IMU spectrogram. Just want to get rid of the orange and the red, and I want blue. So let's turn off the actual notch here so we can see this. This is pre-filter. We can see what's happening, and you can see that a lot of the noise is filtered out. Go back over to Mission Planner, and we're going to search for INS H notch underscore enable, disabled by default. So we're going to enable it, we're going to write parameters, and then we're going to need to refresh parameters. So now let's just take off the underscore enable. Our frequency that we're going to type in here, 325 hertz with a bandwidth of 30 hertz, and the mode to ESC telemetry. We're going to come down on notch options, and we're going to click multi-source and update at loop rate. And then for the ref, we're going to type in 1, the notch harmonics. We only need the first harmonic, and we can write parameters and save. Now that we have the notch filtering set up, the next step in the process is to tune the PIDs. And ArduPilot is really convenient because it has an auto-tune that'll do this for us mid-flight. In order to do this properly though, we're going to need to see some messages, so we're going to need to set up the on-screen display and use either goggles, glasses, or a display screen in order to see those messages when the auto-tune is starting and when the auto-tune is finished. So in order to do this, we're going to come over here to onboard OSD. I'm going to scroll down here. I'm going to use Imperial, and then we're going to come up to screen 1, decrease, HD layout. We just need a basic screen setup for right now. Okay, so all we really need to care about is the messages on the screen, what flight mode we're in, and how much battery life we have. Let's go back over to settings. So we're using a 4-cell battery, average cell, let's go 3.5, critical volts, 3.3, and then we can write. Let's go over to the full parameter list, and we're going to need to set up the on-screen display settings. So we're going to search for OSD underscore type. We're going to choose MSP DisplayPort, and on the MECO Air all-in-one, the VTX is connected to serial 2. So we're going to do serial 2 protocol. It's already set to DisplayPort, and it is already set to 115 baud rate. Let's write parameters, and then we're going to come over and we're going to search for AutoTune, and go here, and we're going to do 1 axis at a time for AutoTune. And then we're going to set the AutoTune to right side 3 rocker position switch on our TBS Tango 2, which will be RC7 underscore option. And we're going to select AutoTune, and we'll set it back to scripting when we're finished. All right, we'll see you out in the field. Okay, we're out in this big parking lot and getting ready to do our auto-tune. I'm going to take off the vehicle and stabilize. I'm going to switch over to altitude hold mode, and then I'm going to switch into auto-tune. And then the auto-tune script is going to twitch the vehicle on the particular axis that we've chosen in Mission Planner. As it's twitching the vehicle, it's dialing in and trying to get a good PID values. And so we're going to repeat the process for each axis, and we're only doing 1 axis at a time. Sometimes the auto-tune takes a couple of minutes, and sometimes it can take up to 7 or 8 minutes. So I'm taking off in stabilize mode. All right, I'm going to try and keep it in the camera angle, and then switch over to altitude hold mode. There is kind of a pretty good breeze here, so I'm going to have to correct this as we go. All right, let's get it out a little bit further, and then switching into auto-tune. And you can see it drifting off camera with that wind. I'm going to bring it back. And then it's going to do the switching for quite a bit. Okay, so AutoTune has finished. We're at 3.45 volts. So what I'm going to do is I'm going to turn AutoTune off. And I'm going to go into stabilize mode. And we're going to just test out this. So this is what it looks like on the old PIDs and on the new PIDs. So definitely a little bit more responsive, old, and new. So what I'm going to do, we're getting down to 3.3 volts. So I'm going to land right where I am. And then when I disarm, the values are going to save. All right, we'll see you back on the computer. Okay, we're back on the computer and the vehicle is connected to Mission Planner. So let's go to the extended tuning tab. And you can see that the roll PID values have changed with the auto tune that we just completed. The next step that you'll want to do is complete auto tune for the pitch axis and then again for the yaw axis. Because we did the roll axis on a windy day, what I will end up doing is going back and redoing the auto tune on a calm day or somewhere indoors. Alternatively, what you can do is run auto tune from loiter mode. So now you have a stable position hold with the optical flow sensor, and that's going to be the third iteration of auto tune that I'll complete. If we go to the Methodic Configurator documentation page, evaluating the performance of AutoTune, you can see here that the maximum gain that AutoTune strives for is 36. In the documentation, the screenshot shows that this individual was able to get a 36 gain for roll, 31 for pitch, and 14 for yaw. On ours, we got 24 for roll. Well, it doesn't matter if you're not hitting 36, that's just the value that AutoTune strives for. Okay, so I'm gonna go off screen and I'm gonna complete the pitch and yaw axes separately, and then I'll be back with the next video in the series where I walk through configuring the optical flow sensor to set us up for using loiter mode or position holding, and I'll also be walking through how to set up some of the Lewis grips to tie everything together on this build. So thanks for watching and stay tuned. Thanks.